All right, we're going to try a new program as well as a new problem. And what we're going to look at is a situation where we are given the position versus time, or position as a function of time for an object. Okay? And it's a pretty arbitrary function. If you graph this out, if you ask Google to do it, or Mathematica to do it, or your calculator to do it, or whatever you want, you end up with a graph that looks something like this. Okay, not a particularly good drawing of it, but you sort of get the general shape. And in general, it's nice to get a visual representation of what function you're dealing with there. Okay, so just to be clear, this graph would be your x versus t. Now, we've already talked a little bit about how you could take a look at this and say, go in and let me grab another color here. Good. And if we wanted to plot v versus t on that same graph, well, we'd look at the slope of the x versus t graph at all these points and sort of graph it out. So we'd have a 0 at the origin, right? Because the slope of the graph there is 0. And we'd have a 0 right about here, because the slope here is about 0. And then everywhere along this portion of the graph, you'd have positive velocities, and they'd start small, they'd get big, they'd start small here, they'd get big here, and they'd get smaller as you approach 0 there. So you might expect something, I don't know, vaguely like that in between. And then everything over in this portion of the graph would be negative and quite steep, yeah? So you'd go directly in, and it would start small, of course, but then get bigger and bigger and bigger, albeit in the negative direction, okay? So that'd be the rough version of the corresponding velocity versus time graph for that. But let's actually get into the calculus of how these all are related. And to drive that, let's ask ourselves a couple of questions. So first, let's find what the v as a function of t would be, and also a, acceleration as a function of time, would be for corresponding to this position as a function of time. So we know that v is the time derivative of this x function. Let me just write it that way rather than the more explicit version. And when we take these derivatives, this is just a polynomial, so we don't have to work too hard here. You have 2 times 5, 10, the time left over, and then you pull the 3 down, 3 times 4, and you get a coefficient of 12. You have a time squared left over, okay? If you look at that and you graph that, it actually doesn't look too dissimilar to the shape of the v graph that we stuck over here, okay? And you can, of course, go through and do the acceleration as well. Remember that acceleration is dv dt. And so if we take the derivative of the function we have for v up there, we just get a 10 minus 24t, right? Okay, simple enough. Just taking some basic derivatives. Now, we can also ask questions like, okay, well, what is the velocity and the acceleration at a particular moment in time? And now that we have these functions, that's really easy. You just evaluate the function at some time. Just to give us an example, let's say that we've got, let's say time equals 2 seconds, just to keep the mathematics pretty simple, okay? What is v? What is a? All right, so when we do that, things go pretty quickly. So we got v at time 2 equaling 10 times 2 minus 12 times 4. And so you end up with, let's see, 20 minus 48 negative 28. And I'm running out of space, so I'll just go meters per second down there. Okay. And for the acceleration, much the same. If you plug all of that in, you end up with a negative 38 meters per second squared. All right. Now, that out of context isn't too informative, but again, we're just getting things more or less familiarized for ourselves in how to manipulate these equations and these derivative relationships between them. We can also ask questions like, okay, well, when is x at a maximum value? Now, this is something that you maybe don't remember as clearly from calculus class, though it's an important bit, and it's certainly something that you went over. Of course, the maximum from our graph of x would be, well, whatever that is, okay? But let's find it quantitatively. And what we're going to do is use the pretty well-established method for finding that. And to find that, we need to find first where the slope of the x as a function of the x function is going to be 0, right? And remember that velocity is the slope of an x versus t graph. So what we want to do, let me grab my eraser here. We'll get rid of this stuff because we don't really need that anymore for this bit, okay? What we're going to do is we're going to figure out when the slope of the x versus t graph is 0. In other words, we're going to find out where velocity is 0. And when we do that, okay, what we want to do is we want to set our velocity as a function of time equal to 0. And that has to equal the velocity function. And we're going to come up with two solutions to this, right? When we divide both sides by t, we can eliminate a factor of t on this side, on the right side. But of course, that means that one of the solutions to this equation is t equals 0. And the other solution we can get by just taking it a step farther. So we end up with something that looks like, like this. Okay, because one factor of t drops out when we divide both sides by it. And that means that the solution that we have here is going to be, well, move that to the other side, divide by 12, you get 10 over 12, which is 5 over 6 seconds, okay? So the question remains, which one of these would be a max and which one would be a min, right? Because it could be either. We could either be here, like we are, at t equals 0, or we could be up here, like we probably will be at 5/6 seconds, okay? To determine that, well, we could just appeal to the graph, right? We could just look over here if we've done the work to look at the graph prior to this, and we say, well, there's only really one possibility there. Formally, right, what you would look at is the concavity of the function at each of those points, okay? And how do you look at concavity of a function? Well, you look at its second derivative. And to compute the second derivative of x, you would take its derivative once and then take its derivative again. And that's effectively what you're doing when you go from here, from x to v, and from v to a, right? So for a is also the second derivative of x with respect to time, okay? So that'll tell us about the concavity. If it's positive, right, we concave up. If it's negative, concave down, and we're at a maximum. So if we grab my eraser here again, make ourselves a little space down here underneath the graph, we can check that. And we'll grab my pen again. And if we look at a at time equals 0, well, then that's just going to be 10 because the second term is in that function. It just goes to 0. So that's 10, positive 10, right? So that's concave up, and that is not going to cut it. That's not going to be a max. That's going to be a minimum. So we can get rid of that. Okay, and so we're kind of hoping that there's a max on the other one, but let's actually work it out to make sure that it works out as we would expect, right? So acceleration at 5/6 seconds. Okay, the arithmetic here is mildly more complicated, but we don't really need to worry too much about it. We don't really have to go through the whole thing. Okay, because we can pretty clearly see that 5/6 of 24 is going to be greater in magnitude than 10, and so this whole thing is going to be negative. That means concave down, CCD, and that means that t at 5/6 seconds is going to be when x is at max. Okay, so these are old calculus skills, shaking a little bit of the dust off for us and relating them to those skills to these x and v and acceleration values. Thanks for your attention. Let me know if you like the format of this video better than some of the other ones, and we'll work from there.